All right, new section. So in this section, we're going to cover what is split into two different sections in your book, 2.6 and 2.8. But really, the basic idea is we're going to stop learning different rules for how to take derivatives, and we're going to start to use some of the knowledge. We're at the point where I can give you just about any function, and you can take the derivative of that function. We spent a lot of time learning various rules and working through some really complicated examples. And you might be getting kind of frustrated, like, all right, I can do this, but why? Well, in this specific section, we're going to talk about what the derivative can tell you about a function, which, spoiler alert, isn't going to be super interesting. It probably won't justify all the work that we've done to calculate derivatives, but as we learn more and more about what the derivative tells us, we'll get to see more and more applications of it, and hopefully eventually you'll see the need for all the hard work that we've done so far. Anyways, let's start out with an example. We got this function f of x equals 1/3 times x minus 2 cubed minus x minus 2 squared plus 20 over 3. I sketched a graph of this function. It's shown down here. I'll go ahead and tack on the arrows to really indicate that it continues forever in both directions. You can even label this thing f of x. And what I want to do is pretend you hadn't taken any calculus at all. Pretend I gave you this graph right here, and I asked you the question, what are some important points on this graph that really describe the shape of this graph? And you'd be like, well, that's a really ambiguous question. I don't know what you're talking about. But maybe if you had to pick some, maybe the points you'd pick as kind of interesting points would be one sort of over here and one sort of over here. These points we'll later call local maxima and local minima, but at this point you might just be like, yeah, they're kind of interesting. It's where the curve sort of turns around. And maybe I'd press you on that a little bit and be like, what do you mean turn around? And you're like, well, everything to the left of this point, the curve is going up, and then to the right of this point, this curve is going down. And then we hit this point and it turns around again and starts going back up. And I'd be like, that's perfect. That's exactly what I'm looking for. The first thing that we want to do is make concrete this idea of going up and going down. The terms we're going to use for that are increasing and decreasing, and the term that I'll use when it's neither increasing nor decreasing, like at these specific points, is I'm just going to refer to it as flat. So maybe if I gave you this graph with no real context, you'd be able to look at it and tell that the graph appears to be flat here at x equals 2, and again at x equals 4. And the graph is increasing, in other words, going up as you read it from left to right, everywhere to the left of 2, which we could write as from negative infinity up to positive 2 if we were using interval notation. And then again, everywhere to the right of 4. So I can put my union symbol and then say everywhere from 4 to infinity. If I wanted to write an interval notation where this graph is increasing, just by looking at it, I'd say that it's increasing from negative infinity to 2, and again from 4 to infinity. And where is it decreasing? Well, it's decreasing when it's not increasing or flat. It's decreasing in between 2 and 4, which in interval notation I could write like this, 2, 4. We're increasing over here and also over here, and we're decreasing in here. And because this graph is continuous and differentiable, the only spots it can switch from increasing to decreasing or decreasing to increasing is where it's flat. So we're flat at these points where it switches. And you're like, yeah, I get the point. That's not that interesting. Okay, stick with me. What if we didn't have this graph? Or what if we didn't trust that this point where it appears to switch from decreasing to increasing was exactly at 4? Maybe it looked like it was 4.1 or something and we weren't positive. Well, if we really cared about where it was increasing, decreasing, and flat, what we could do is take advantage of the fact that we have the equation of the function, f of x here. Since we know the equation of the function, and we know that the derivative talks about the rate of change of the function, it makes sense that we could figure out the derivative of this function if we were interested in figuring out where the graph was increasing and decreasing. We spent so much time learning derivatives, we might as well do it. Let's say if we had to find the derivative of this thing, we'd recognize that we have 3 different terms. So we take the derivative of each term individually. For this first term, this 1/3 is a constant, so I can pull it out in front. And then I have to take the derivative of x minus 2 to the 3rd power. Using the chain rule, I first take care of the 3rd power by bringing that 3 down in front and leaving the x minus 2 alone. Subtracting 1 from the exponent leaves me with x minus 2 squared. But then I'm not done, kind of. I still have to multiply by the derivative of this inside function, this x minus 2. Fortunately for me, the derivative of this inside function is just 1, because the derivative of x is 1 and the derivative of 2 is 0. So the derivative of this first term is 1/3 times 3 times x minus 2 squared times 1. What about this second term? Well, it's kind of the same idea. I'll leave the negative alone. I'll bring the 2 down in front and write x minus 2 raised up to the 1st power using my power rule there. And then I'll multiply by the derivative of the inside. The derivative of x minus 2 is, again, 1. And then finally, the derivative of this last term, well, it's just a constant. So the derivative of 20/3 is just equal to 0. I could clean this thing up a little bit and notice that this 1/3 and this 3 cancel out. So this first term is just x minus 2 squared. And in this second term, I don't need to write the 1 here nor the 1 up here. So I could just write minus 2 times x minus 2. F prime of x is equal to x minus 2 squared minus 2 times x minus 2. Now that I know this derivative, I can figure out where my function is flat without looking at the graph at all. The function is going to be flat when the tangent line to the graph at that point is horizontal. In other words, the slope of the tangent line is just equal to 0. So if I take f prime of x and set it equal to 0, I can solve for x to find, hopefully, these 2 points. Let's see if it works. I got x minus 2 squared minus 2 times x minus 2 equals 0. And I want to solve this equation. There's a few different ways you could do it. You could expand things to get rid of the parentheses. But if you're kind of clever, you might notice that you have an x minus 2 in each of these terms. So you can factor out an x minus 2 from this term and an x minus 2 from this term. And what would be left? Well, from this term, we'd still have an x minus 2 because there were 2 of them because it was squared. And from this term, if this x minus 2 is gone, I just have a minus 2 left over here. So I can factor this equation in this form. And since x minus 2 is just x minus 4, figuring out when f prime of x equals 0 is equivalent to figuring out when x minus 2 times x minus 4 equals 0. Great thing about this equation is I have a product of things equaling 0. That can only happen when the first thing, the x minus 2 equals 0, or the second thing, the x minus 4 equals 0. So that can only happen when x equals 2 or if x equals 4. What did I just figure out here? I'm trying to figure out when f prime of x is 0. And I figured out that the solutions to that equation happen when x equals 2 and when x equals 4. F prime of x equals 0 corresponds to the slope of the tangent line being equal to 0. So the slope of the tangent line equals 0 at 2 and 4. When the slope of the tangent line equals 0, the graph is flat. So I can confirm what I figured out right here. And it's worth pointing out that things don't stop there. If I was interested only in where the graph is increasing, what I could do is solve to figure out when f prime of x is greater than 0. Solving f prime of x is greater than 0 is kind of complicated. Solving inequalities when your function is quadratic is a little bit challenging, but the easiest way to do it, I think, is to make what's called a sign line, where you kind of draw a number line here. Maybe here's 0 and 2 and 4 and 6. And then you recognize that since solving this inequality is so hard, what you can instead do is solve the equality f prime of x equals 0. Well, fortunately, we already did that. F prime of x equals 0. The solutions to that are at 2 and 4. So when you're solving the inequality, you take the solutions to the equality and you kind of break up your number line at those points, 2 and 4 in this case. I'm interested in when my derivative is greater than 0. That's going to happen on intervals, and it's only going to change from being greater than 0 to less than 0 at points where f prime of x equals 0. So it can only change at these dotted lines. What that means is I can just test a number in this region, and if f prime of x is greater than 0 at that number, then it must be greater than 0 at all numbers in that region. So because I have 2 solutions to the equality, my number line is broken up into 3 different regions. Maybe I'll call them regions 1, 2, and 3 respectively. What I want to do is pick any number in region 1. It doesn't matter which number. I could pick 0, I could pick 1.99, I could pick negative 500, any number that I want that's in region 1. I'm going to pick 0 because it's easiest, and I'm going to evaluate f prime of 0. To evaluate f prime of 0, I copy exactly what f prime of x is equal to, except I change all the x's into zeros. So I get 0 minus 2 squared minus 2 times 0 minus 2. What's this thing equal to? Well, let's see. 0 minus 2 is negative 2. Negative 2 squared is positive 4. And then from positive 4, I want to subtract 2 times negative 2. Well, negative 2 times negative 2 is positive 4. So I get another 4. 4 plus 4 equals 8. I don't really care that this is equal to 8. All that I care about is that 8 is greater than 0. What that means is that at this point 0, the derivative is 8. So at this point 0, the derivative is positive. And because the derivative can't switch from being positive to negative at any point until we get all the way over here to 2, what that means is for all numbers in region 1, the derivative is going to be positive. What about region 2? Well, I can do the same argument. I can figure out f prime of any number that I want that's in between 2 and 4. 2.1, 3, pi, whatever you want. I'm going to pick 3 just to make the calculations a little bit easier. And what I got to do is put 3 into this machine and see if a positive number comes out or a negative number comes out. Well, let's see. If I put 3 in, I got 3 minus 2 squared minus 2 times 3 minus 2. What's this thing equal to? 3 minus 2 is 1, and 1 squared is just 1. Minus 2 times 3 minus 2. Again, 3 minus 2 is 1. Negative 2 times 1 is negative 2. So I got 1 minus 2, in other words, negative 1. I don't really care about the value of this thing. I just care that this thing is less than 0. I'm trying to figure out when f prime of x is greater than 0. At 3, f prime of x is not greater than 0. What that means is for all numbers in this region, f prime of x is not going to be greater than 0. I do this one more time over here in region 3. There we go. By picking any number that's greater than 4. I'm going to pick 5 just to try to keep things simple. I got f prime of 5 is equal to 5 minus 2 squared minus 2 times 5 minus 2. Let's see, 5 minus 2 is 3, and 3 squared is 9. From that, I want to subtract 2 times 5 minus 2. 5 minus 2 is equal to 3. 3 times negative 2 is negative 6. So I got 9 minus 6, in other words, 3. Again, I don't care about the value of this thing. I just care that this thing is greater than 0. Because the derivative at 5 is greater than 0, the derivative at all points in region 3 must be greater than 0. If all I cared about is when the graph was increasing, and I didn't have this graph right here to reference, what I could do is solve this inequality. There's lots of ways to solve inequalities. Most of them are pretty difficult. Probably the easiest way is to set up this, which is what's called a sign line, by solving this inequality, taking the solutions, and splitting your number line up into regions based upon those solutions. From this sign line, I see that f prime of x is greater than 0 in regions 1 and 3. Region 1 is all numbers that are less than 2, in other words, the numbers from negative infinity up to 2. And region 3 is all of the numbers that are greater than 4, in other words, from 4 up to infinity. You could do a similar argument to figure out where the function was decreasing if that's what you were interested in. This little interval in here from 2 to 4, we could figure out by solving the inequality f prime of x is less than 0. How would you solve that inequality? Well, you'd recognize that solving inequalities is pretty hard, but solving equalities isn't too bad. So you'd solve this equality where you get the two solutions 2 and 4. You'd set up this sign line. You'd test numbers in regions 1, 2, and 3. And now you'd be looking for regions so that the output of the derivative is a negative number. That only happens between 2 and 4. So we get that the function is decreasing between 2 and 4. The point is just supposed to be that if you have a function, it's going to turn out that it's really useful to know where that function is increasing, decreasing, and flat. And we can do that if we have graphs, but graphs have limitations, right? Sometimes you don't have the graphs, and they're only as accurate as you draw them. So sometimes it's really beneficial to do things algebraically. And we can do this algebraically now that we know how to calculate derivatives. It's a little bit challenging because it involves solving inequalities, which frankly nobody really likes. But once you get the hang of this method, it's not too bad, and that allows you to confirm these answers. I got to be honest, I wasn't super excited to teach this part. I don't think it's super interesting, it's not super fun, but there is something that I think is kind of interesting. We calculated the derivative, right? F of x is this expression, f prime of x is this expression. This expression is a function. The derivative is itself a function. I have the equation of that function written right here, but there's no reason I couldn't look at the graph of that function. And the graph of that derivative function on the same axes as the graph of the function itself is really interesting to look at. Here's a picture. In blue, we have pictured f prime of x, which as we figured out above is x minus 2 squared minus 2 times x minus 2. In red, we have the same function as above, f of x equals 1/3 times x minus 2 to the third power minus x minus 2 squared plus 20 over 3. What we talked about earlier are the points on the function that we're really interested in are the points at which the function is flat. And we're also interested in knowing when the function is decreasing, like it is in this case between 2 and 4, and when the function is increasing, in this case everything to the left of 2 and everything to the right of 4. But now that we have the graph of the function and the graph of the derivative, we can make some observations. These points at which the graph of the function were flat correspond with points at which the graph of the derivative has an x-intercept. Oh yeah, that makes sense. If the output of the derivative is 0, then the slope of the function is going to be equal to 0. So the fact that the graph of the derivative has x-intercepts at 2 and 4, and the graph of the function is flat at 2 and 4 is not a coincidence. That's always going to happen. Furthermore, the fact that the derivative is negative in this interval where the function is decreasing is not a coincidence either. Anytime the derivative is negative, the function is going to be decreasing. And anytime the derivative is positive, like it is out here on the outside, the function is going to be increasing. It takes a while to get comfortable with looking at the two graphs kind of in conjunction, but if there's one takeaway from this video, it's this little sentence. The height of the graph in blue, the height of the derivative, tells you the slope of your function f of x. When the height of the graph in blue is a positive number, the graph in red is going up. It takes a while to get comfortable with this, and I'm not using very precise mathematical definitions here, but I think having this idea in mind will really help you keep straight what you're looking for when you look at the graph of the function versus the graph of the derivative. And if you're thinking, that's not too bad, like I'm always just looking for the height of blue and I'm always looking for the slope of red, well, unfortunately, it's not quite that easy, because what you'll see in the next video is the analysis that we did on the graph in red, we can also do on the graph in blue. If I asked you about important points without giving you a concrete definition of the graph in blue, you might pick this point right here, where the slope of the tangent line to the graph in blue is 0. You might want to know when the graph in blue is increasing. When blue is increasing versus blue is decreasing, what does that tell you about the graph in red? Fortunately, maybe for you, that's the second level of abstraction of this section where things get a little bit more difficult, and I'm going to save that for the next video.